väärtusmeetmed.
Okay, so let's start again. So I have read quickly the comments on Discord. So, but a bit too quickly to make very specific answers. But there were questions. So the first question is easy to answer. Is I have used two symbols for the same thing. In the first slides, I used NAT, and then I used the mathematical symbol of the natural numbers. Of course, the intention is that this is the same type, except that NAT was more referring to notation used in functional programming, and the notation natural numbers is referring to the notation of the hot book, which is more mathematical. Okay, but it's the same type. And then there was a question: is what are judgments? Okay, so well, I don't have a philosophical answer to that. It's just that type theory is built on a number of syntactic gadgets. Okay, so there's a gadget called types, and then there's a gadget called terms. Okay, and then you assemble rules that say that a term has a given type, and those rules are expressed in forms using judgments. So, for example, in these few rules here, okay, you see that everything here, these are judgments. Okay, and in a judgment, you see types, elements of types, contexts. So this is the language of type theory. It's a kind of grammar. If you learn French or English, you will learn verbs, nouns, etc. So this is the grammar. The grammar is that you have types, you have terms, you have contexts, and you have a way to assemble them to form judgments. Okay, and the rules, the important thing is that the formal rules of type theory derive judgments from other judgments. Okay, so I hope this will help. And then about the difference between the two kinds of equality, well, you will, again, it's difficult to be too philosophical. At the beginning, you will learn to see the differences, but the idea is that in the definitional equality, for the definitional equality, I will provide, I provide some, as time progresses, I will provide some ways to derive definitional equality. So here we have beta reduction. When time will come for other types, we will have other kinds of definitional equalities. So progressively, we will learn how to show that two terms are definitionally equal. And then equality types is at a different level. It's a type. And what we want to learn is not to equate in a type. Well, maybe I write it here. In a type A, no, like this. In a type A equals A, B. The rule of the game is not so much to have a sequence of terms relating A to B, which is what happens in definitional equality. You have really a sequence of terms using, well, it's equational reasoning, as you may know. Okay, here it's different. Here we have a type, and we are interested in producing elements of this type. Okay, and even more interestingly, we will be interested in defining functions from equality types like this into some other type C, and we will see this in the future. So what we will do with equality types is quite different in nature, and you will experiment this very shortly when I will discuss sigma types. Okay, so let me delay other comments on the difference between definitional and propositional equality until I have described the sigma types, because you will see here something interesting. Okay, so let me erase this and continue. Okay, so my next slide is about illustrating the pi type, but actually it's, yes, okay, yes, it's an illustration. So suppose that I have a family of types, C, that depends on a type A and a type B, and while, well, B does not depend on A, and A does not depend on A. Sorry, B does not depend on A, and A does not depend on B. So this is summarized by this information here. Okay. So A and B do not have dependence, but C depends on both A and B. And we are interested in functions in this pi type. Okay, so function that takes an argument in A, an argument in B, and returns a result in Cxy. And I want to describe the function swap. Okay, what this swap function does, it will swap the arguments of H. Okay, so the intention is that swap okay, A, B, C, H, XY will be definitionally equal to H, Y, X. Okay, so how do we program this function? Well, it's written here. It's nothing fancy. Okay, so it's just to experiment with all the lambda notation. Okay, so swap takes an argument A, an argument B, an argument C, okay, an argument H, okay, like here, and then okay, and then okay, then I wrote it in a different way. Okay, so let me change to match what I exactly wrote. So it's a variation. I wrote something a bit different, but it's exactly, of course, exactly the same. I wrote Yx and here Xy. Okay, so again, so it takes a Y, it takes an X. Okay, so you should read really this sequence of lambdas as saying exactly the same thing as here, and the result is Hxy. Okay, and what is the type of this? Well, the type of this is that it takes an A, takes a B, takes a C, takes a function H, okay, and returns a function, okay, which has this type. Okay, so the swapping here has also to be reflected in the type. Okay, because the type of swap Yx, okay, is not Cyx but Cxy. Okay, so this you see that you also swap the order of the arguments. So the best is to read this type by yourself, but this is an illustration of how to play around with pi types. It's nothing very important. And just to mention an important term, such a function that is that does not use any specific information about A, B, and C, okay, but just plays around switching arguments, is called polymorphic because its code, okay, doesn't need to know what A is, what B is, and C is. So this is what polymorphic is about. And functional languages like OCaml or other dialects of ML are typically polymorphic. Okay, so our next type is coproduct type. Okay, so coproduct, I will follow the same plan. First, an introduction of the type itself. So if A is a type and B is a type, then A plus B is a type. Then how do I construct elements of the product type, the coproduct type? Well, if A is an element of capital A, then it is also an element of A plus B, but I tag it with an in left. So I in left A, and this produces an element of A plus B. Or I tag an element of capital B with an in right, and I say in right B is of type A plus B. So these are the ways to introduce elements of A plus B. These are the constructors. And now comes something called induction operator. Okay, so here you should interpret the word induction in a more liberal sense than the one you probably learned from elementary mathematical reasoning. So usually you speak about proving a property by induction on natural numbers, and then you have the idea of some recursion is going on. But here induction is taken in a more general sense, which is the following. So I will speak of induction each time I produce you, I give you a principle. So this principle is given together with the type. And what does this principle tell you? It tells you how to build a function out of the type I'm considering. So here, the type I'm considering is a coproduct type. So my question is, how can I build a function from A plus B to C? Or more generally, how can I construct a function from a type C to a type C that depends on A plus B? So how can I construct a function from a dependent function from A plus B to C, so a function of this type? And the answer is, well, let's do the non-dependent case first. The answer is, and this comes from elementary mathematics, I would say, think of E plus B as the disjoint union of E, A, and B. So if I want to define a function, so here, okay, let me do this like in an elementary course on set theory. This is A and this is B. And I want to build a function that goes to C. And you see, okay, and C is something like this. You see that to define that function, I should give a value in C for each element coming from here and for each element coming from here. So what I need is a function from A to C, and I need a function from B to C. And this is all I need to build a function from A plus B to C. And this is exactly what is written here in the more precise language of type theory. So first of all, this should be, this principle should hold for any type C depending on A plus B. So here, this was a non-dependent case, but here it's dependent case. So given a family of types over A plus B, that's the first item here. Given a function that goes from A to C, okay? But the precise way to state it is actually a function living in P pi A of type capital A, C of in left of A. So I have to be precise because C depends on A plus B, and A is not a member of A plus B. It's a member of A plus B, provided I have tagged it as in left. Okay, and same thing here. Given a function from B to C, okay, expressed precisely in this way, then I have a function from A plus B to C. Okay, so the principle here tells me a way to build a function from A plus B to C. Okay, and this way is provide me with a function from A and a function from B, and then it will be enough. Okay, so this is the induction principle associated with the coproduct type. And then also associated with the induction principle come two definitional equalities. So you see that most of the type formers will come with definitional equalities. So as we progress, we will have more ways to derive things, to compute and to show that things are definitionally equal. So here, well, here it says that actually this function here should, when provided an input in this function here, when provided an input in A, should behave as S. This is what is written here. And when it is provided with an argument coming from B, it should behave as G. Okay. Now, type of Booleans. Okay, the Booleans is an instance if we know already the type 1, but we don't know it already. Okay, but suppose we know the type 1. Okay, so some of you know the type unit in ML or something like that. It's the type 1, which we will see in a moment, is essentially the type with only one element. And Booleans should be just the same thing as 1 plus 1. Okay, but we can also introduce it directly, axiomatically. So it's just an exercise in this style of things. So we can declare the type of Booleans as primitive. So there is a type called 2 for Booleans, which has two constructors, 0 and 1. And the induction operator associated to Booleans says that if you want to find a function out of bool, so a function in this type here, where again C is a type family depending on the type 2, then the only thing that you have to provide is a value for constructor 0 and a value for constructor 1. So this is exactly what is written here. If you provide me with a type family depending on 2, if you provide me with 2 elements, one of C applied to 0 and C applied to 1, because it's dependent. So you must provide the right value at the right instance of this family. Okay, so this will be the value at 0, the value at 1, and since morally speaking 2 has only these 2 elements, that's all you need to define a function from the whole of 2 to C. Okay, and of course you will have these 2 definitional equalities, which says that if this function is applied to 0, then it should return C0. If it is applied to 1, it should return C1. Okay, the sigma type. So type forming, if well, it's mimicking the pi type. if A is a type, if B is a type depending on A, then sigma X dot C the column type capital A Bx is a type. Second thing, what are the constructors? The constructors are the pairs. Okay, so if A is an element of capital A, and if B is an element of capital B applied to small a, then the pair AB is in the sigma type. Okay, and the induction operator is written here. So since this is a real one, okay, but in order to make it more progressive and more pedagogical, I will start from this one. Okay, so these are successive generalizations of the same principle. So first, in the first thing here, I just want to explain how to define a function that goes from A times B to C. Okay, remember, oh yes, there was a question. There was a question in the Discord, which I can answer now. Somebody asked if for example, if the product type A cross B is really the same thing as a sigma type, and the answer is yes, it is by definition. So we could really write like a symbol like this. It's definitionally equal to the type sigma X E A, and here I will write B prime. Okay, what is B prime? B prime is the family. So B prime is of type A arrow U and is defined as, again definitionally, B prime is defined as lambda X dot B. Okay, so this is a non-dependent case. B is a type that does not depend on A. B prime is the constant function from A to U that that provide a kind of fake dependency of B with respect to A. Since B does not depend on A, a way to say this is that B prime is a constant function. It does not depend on A. Okay, and then this is the official definition of A times B. It is the sigma type. It is this sigma type. Okay, where B prime is defined as lambda XP. Okay, so I can write, yes, okay. And then of course, it's the same thing. It's a game in beta reduction, because B prime being lambda XB, okay, if I apply lambda XB to X like written here, okay, this guy is exactly the same thing as B. Hence, we can safely write sigma X A B. Okay, so in other words, sigma X, the sigma type, this sigma type here, is in the case where B is a constant family, returns exactly the usual product. Okay, so the product type is not just the non-dependent analogy of the sigma type, it is just the instance of the non-dependent instance of the sigma type. Okay, it's not an analogy, it's strictly the same thing. Okay, so now let's go back to our induction principle. So the first thing is what I call rec here. Okay, and what does it say? It says that I have type C, okay, that does not depend on A and B, okay, and I have that B does not depend on A, okay. So I have no dependencies between A and B, okay, and I have a type C that does not depend on A and B, okay. So no dependence at all. And here there is an induction principle, so that applies to the usual product, and has nothing to do with dependent type theory, which says, how can I build a function from A times B to C? The answer is, provided you give me a function from A to B arrow C. Okay, so you see here that we already know what arrow types are. Okay, so this thing is supposed to be known, and we want now to know, how can I build such a function from A times B to C, because A times B is something new. Okay, and the idea is that, well, okay, it's kind of officializing the notion of currying. So if you give me a function in uncurried form, if you give me a function in curried form, then this provides a function from A times B to C. In other words, this rec here is the same thing as uncurrying, which is the reverse of currying. Okay, so to build a function from A cross B to C, just give me a function from A arrow B arrow C. Now, suppose that my C here, so this was my first attempt here. Okay, suppose now that my C is depends on A times B. Okay, I will write essentially the same thing. Okay, and I will call this the induction principle on A times B. Okay, I will insist a bit later about this difference between ind and rec. Okay, so yes, so the difference now is that C depends on A times B. Okay, so what I'm looking is for a way to define a function of this pi type, okay, whose domain is A times B. And again, the answer is by giving a curried version of a function. So, okay, so this is for all C depending on A times B, provided you give me a function that returns an element of C of xy for each x in A and y in B, then I have a function from every element of A times B to C. Okay, so a way to read either this or this is to say, well, there's nothing else in A times B than the elements that are pairs of two elements. Just in the same way as here, there are no other elements in A plus B. A way to read this, essentially, is that there are no other elements in A plus B than those coming from A or those coming from B. Okay, so this is the induction principle for A times B. And now, if B depends on A, then it's exactly the same idea, but with more sigma and pi types everywhere. So let's read it, but it's the same idea. So you have dependency of B on A. This is written here. You have dependency on C with respect to A and B. This is written here. C depends on the sigma types, this sigma type, so which compresses A and B together. And we want to get a function out of this sigma type. And in order to provide such a function, because every element here is actually a pair of an element of A and an element of Bx, or an element X of A and an element Y of Bx, to provide such a function is the same thing as to provide a function that takes an X, a Y, and returns an element in C. Okay, and the definitional equality reflects that. It is exactly the equation of currification that I gave before. Okay, so think this really as being the uncurrying of F. So F is a function that takes A and then B. Its uncurried version takes A and B in one shot as just one single argument. Okay, good. So this is the sigma type. And okay, so let's experiment a little bit with the sigma type. So you see here that I have two definitional, I have one definitional equality here. Oh, here, yes, I should not write, this should be corrected. Yeah, I should make a comment here. So I also, I use two notations, well, three notations. There's this notation, okay, propositional equality. This is definitional equality, and this one, which is definitional equality in the very sense of definition. Okay, so I don't know if I say lambda xx, I want to give it a name, so I call it id. Then I will write like this, because I use id as a macro for lambda xx. So it's a definitional equality where on the left I have a symbol, a new symbol or a new identifier, which is by definition definitionally equal to the right hand side. So it's just the same thing as here, with the idea that we are really defining the right hand side from the left hand side as being the right hand side. So here we don't here we do not want this, okay, but here we want this. No, come on. This is also incorrect. This is a type of end. Okay, there are lots of small mistakes. Sorry. Yes. Yes. These induction operators are given and have this type. I will correct all this tonight. Okay. So now, when you see products in programming or in mathematics, if some of you know a little bit of category theory, then you will probably have seen products together with two important functions called the projections. Okay, which we write here as PR1 and PR2. This is what you associate naturally with the notion of product. So here, what I want to show to you is that the induction principle here, described in this slide, allows me to define. And here I really use this column definitional equality in the right setting. So I have a way to define the projection as a macro, whose definition is given here. And same thing for the second projection. It's defined exactly like here. So what is, in order to give a function from A cross B to A, remember that by induction, what I need to provide is a function from, so I take this one, is a function from A to B to A. Okay, and most of the time, this is a convention that you find in many programming languages. Usually, you do not write the parentheses. Also, you do not write the parentheses. So usually, you omit this, and it is the binding. The parentheses. The order of priority of parsing this expression is that you should put the parentheses as they were. Okay, so this by default will always mean this. Okay, So what we want is the function like this, but we have one. This is a function that takes x, y, and returns x. It is here. Okay. And similarly, for the second projection, I need the function that takes x, y, and returns y. Okay. And then, well, I leave it to you to check, because you see that you have to be very precise in instantiating the induction or recursion. You have first to provide a type, okay, because you have to apply to some type, family C, okay, and you have to design the appropriate family, okay. So here I leave it to you to check that the appropriate family to use for PR1 is this family, the constant family, which returns A for each A, where A here varies over, it's written here. The A here, the small a, varies over this type here, okay? And the type family to which the induction principle here should be applied first is this one, okay? I leave it to you to check that this is correctly typed and that everything type checks properly. And okay, so here I give exact justification, but I don't want to read it word by word. When you have the slides, you can check this by yourself. It's important to type check things because this is a way to understand them. Okay, and then you can easily show that this definitional equality here implies these two definitional equalities that you expect from projections. Of course, you expect that projecting the first projection of a pair gives the first element of the pair, and the second projection of the pair gives the second element of the pair. But the idea is that this is derived from the definition of PR1 and PR2, PR2 respectively. Okay? And there is another equality that sometimes is associated with the product. Okay, and this one is called surjective pairing. And this equality, well, is an equality between an arbitrary element Z of the sigma type and the pair formed by first taking the two projections and then pairing them. So the idea is, in terms of data structures, the idea is that you destruct Z, okay? Well, PR1, yes, PR1 and PR2 provides a way to destruct Z, okay, and retrieve from Z an element of A and an element of BX. And then you can construct, after this destruction, you can reconstruct a pair. And what you would expect is that these two things are the same, okay? Now, you have two possibilities here. Either you think that this equality is very, very important to have to be able to compute with it, okay? And then you put a definitional equality. But a more clever thing is to notice that you don't need to put a definitional equality in the sense that you get for free the propositional equality. So what we are going to do in the next slide is to prove. So this is very important, the difference between definitional and propositional equality. Definitional equality, you prove it by essentially applying successively already known definitional equalities. And now we are going to prove a propositional equality, and we will see how we prove it. And that will you will learn something about propositional equality by following this slide, which I will do very, very slowly, because I think this is the key to understand what equality type brings you. So I'm going to provide a term of this type, which will witness this equality. So an equality type is witnessed by providing a term of the associated equality type. So let's see how we can build such a term. So we will apply the induction principle to some situation. So remember, in order to apply the induction principle for the sigma type, we need to find a nice type family, and then we need to find a nice function in the curried form, so as to get a function from the uncurried form. Okay, so I will define a family C depending on, so remember what we need, it's here. We need a family C depending on the sigma type. Okay, so here is this family. It takes a Z, so this Z is in the sigma type. Okay, so this belongs to sigma X A B X. This Z belongs here. And returns, it must return a type. And the type it returns is the identity type or the equality type Z equals PR1Z, PR2Z. So essentially, what I wish to prove, I turn it into a type family. That's a very, very common pattern that we will meet later. So this is a perfectly well-defined family of types. And now I need to find a function that, okay, so how should I read this? Now I need to find a function. Yes, so I need to find a function which is written here. This function here, okay. What it should have the type pi x of type A. Let me repeat what is written here. Okay, pi y of type bx, and then it should have the type cxy, right? Cxy, yes. Okay, so let's see if we have such a function. Well, what I pretend is that yes. So you see that this family is defined for, yes, for an arbitrary Z. Okay, so Z is a kind of black box of type of sigma type. Okay, now the idea here is that if I open this black box by instantiating this Z to be a pair XY, okay, so if I write CXY, did I write it? Yeah, I didn't write it, so maybe I write it. So you see that if I write CXY, okay, so I apply this lambda term to XY. So I replace Z by XY. Okay, so let's be very explicit. because this is a key example. So let's do it very slowly. So I replace everywhere Z by XY. Sorry to be slow for those who are very quick, but some of you are not the quickest, so maybe it's good to not to be too quick. Okay. This is exactly what C applied to XY is. It is this equality type here, okay, where Z has been replaced by XY, okay. But now, definitionally, this guy is equal to X. This guy is equal to Y, okay. Hence, you see, it's also written here. It's also written here. The left-hand side here is definitionally equal to the right-hand side, so that reflexivity, which is a proof that XY is equal to XY, by the same trick that we've seen before, is a term of type C of XY. Okay, because this, it's exactly what we wrote before. If A equals, remember we wrote before that A equals B definitionally, implies that ref is of type A equal B. This is what we've done before. So for this same reason, we have that ref XY is a proof of C of XY. Hence, we have a perfectly well-defined function of this type, which is written here, which is lambda XY, ref XY. Applying the induction principle to this family C and to this function produces a function of this type, okay? And now, if I apply this function to Z, I get an inhabitant of CZ. But what is CZ? It is this type. So we have provided an inhabitant of this type. Hence, this equality, the surjective pairing equality, holds propositionally. Okay. So you see that to prove a propositional equality is a very, very different kind of game as proving a definitional equality. And the induction principles provided by type theory will give us very powerful tools to derive propositional equalities, which are weaker than definitional equalities, but you have powerful tools to prove them rather than having to assume a definitional version of equality. So why would you care? That's the idea. Why would you care to add explicitly surjective pairing as a definitional equality if you get it for free as a propositional equality? That's the moral of this story. Okay. So now let's continue and look at other types. Okay, so the type 1 has been announced. Okay, so it's a type with only one element. Okay, so it's a type, and we call it 1. It has only one constructor. We call it star. And the induction operator is easy. If we want to provide a function from 1 to something, okay, where C is a dependent type family on 1, okay, well, this type family is not really dependent, but formally it is, okay, because one is too small to hide real dependencies, but anyway, there is an induction principle. And it says that C is a type depending on 1. If I want to provide a function from 1 to this type, it's only required to provide one element of C. Okay, so you provide an element of C applied to star. So because C depends on one, you provide an element of C star, and this is enough to define the function everywhere. Okay, so essentially one morally contains only one element. And then 0, okay, 0 is the same ID, but this time there is no constructor. So 0 is the empty type. So there should be no constructor, but there's still an induction principle. Okay, and this induction principle it has a lot to do with there's a principle in logic which says that if you assume something false, okay, if you have a formula that you know is false, so let me write it false, then from this formula you can derive any other formula. Okay, this is a principle in logic. Once you have a contradiction, everything is contradictory. That's more or less the idea. Okay, good. So why is this related to the 0 type? So essentially 0 can be thought as false, as the absurdum, because, well, it's empty because it doesn't have a proof. Okay, but you can always assume, okay, in a context you can always assume that there is an X of type 0. So you could build a context like this, okay, and this begins to look like this. Okay, so this thing here begins to look like this. Okay, assuming the presence of a variable X of type 0 in the context is the same thing as assuming false. And then the idea is that without any other assumption, okay, so under the assumption that I have a family depending on 0, under the assumption that I have an X of type 0, then I have a function that goes from in this type. Okay. Now I have an element of this type, or if you prefer, assuming that I have a type depending on 0, I have always a function from 0 to from 0 to D. Okay, and this is, well, you have, yes. There's another analogy here which I could draw here. If you have gamma in your type system, if you have gamma proof A of type A, okay, in the mathematical world, this is the same thing as having a function from gamma to A, okay, or an implication that gamma implies A. Okay, but gamma is not a formula, but okay. I think you see the idea. So this is really saying that you get for free functions like this, because from the false you can derive everything. Okay, this is the idea of this induction principle, and let's see how we can apply it. We can apply it to prove the following thing. You can apply it to prove that for all X and Y of type 0, so you can always assume such a thing, even if you will, it's a variable, so you can always assume such a thing. Under this assumption, we have a proof that X is equal to Y. So if by case there were elements in 0, I at least know that they are all propositionally equal. Okay, and we will see that such a type, which has this property, is called a proposition. So 0 is a proposition. We will see this tomorrow. So, but I can anticipate here. This says that 0 is a proposition, and we will see exactly what this means formally in homotopy type 0. This is for tomorrow. Anyway, so how do we prove that any two elements of 0, if we assume they exist, are equal? Just by applying induction, okay? Because, okay, yes, I need to find a family, D, okay? But this family, well, this family can be defined here. It's here. No. So I need to find a family depending on 0. So yes, this is a trick that we will use over and over. If we assume that X is of type 0 and Y of type 0, we can give slightly different roles to X and Y. We can decide to fix Y and to let X vary. So we can define a type family dx as dx is the equality type X equals Y. So it depends only on X because this Y has been frozen, it has been fixed, okay? So this defines, dx defines a type family depending on 0, okay? Because it depends on X, which is of type 0. So D is correctly typed, okay? So the induction principle tells me that if I apply in the induction principle to D, and then to some element of 0, but I have one, which is X. So if I apply this, I should get an element of dx, okay? I mean, I have an element of dx. Again, here, it is of type. Yes, and the answer is that this guy has type dx. This type, yes, this guy has type dx. But what is dx? It's x equals 0, y. So this is a term of this type. So we have proved that this propositional equality holds. Okay, so now in the rest of the lecture, we will look at natural numbers. Let me check. I have less than half an hour, so I hope to cover natural numbers. Let me anticipate. Yes, natural numbers, and identity types. Okay, so I will probably, I have been a bit slower than what I expected, so I will probably not give every details. Yes, okay. So there are two important types to come, okay? The type of natural numbers and the identity type, okay? And I will probably be a bit sketchy on the users. Yes, I will try to cover both. So let's start with type of natural numbers. So we follow the usual pattern. There is a type called nat, okay, and written n. There are two constructors associated with this type, which are 0 of type nat and sux, which is a function from nat to nat. So this way of presenting natural numbers goes back to a logician of the end of 19th century, I believe, or early 20th century, called Peano. So this is a Peano presentation of natural numbers. And then you have the induction principle, okay? And now, by now we are a bit used to induction principle. And this one is really inductive in the more traditional sense, okay? Because there is some kind of recursion. So suppose we want to find a function from natural numbers to some type C, depending on natural numbers. What we should provide is a value of this. So we want to define this function. We should define its value on 0. So we should provide an element of C0. and we should provide a way to compute the value of this function at n plus 1. Okay, and this knowing the function for values lower than n, and this is provided by that second component which I provide, which is a function that takes a natural number, an element of n, and returns an element of c of n plus 1. Okay, and the best way to understand how this works is to see the definitional equalities associated. So the value of my function defined by induction at 0 is given by this component here. Okay, so it's C0. The value of my function at sux n will be computed from the value of my function at n, which is here, using the function cs. So this, I will use the function cs, which I will apply to n and to the inductive result of applying the function I'm currently defining to n. So you see that this is a recursive definition, but okay, technically it's called primitive recursive. And this primitive recursive definition is obviously terminating in the following sense, is that if you see that you cannot apply this definitional equality forever because this n decreases. So in other words, a function computed by this principle, which is called a primitive recursive function, is a function that terminates, or if you prefer, that is total. And if you know a little bit of recursion theory, there are many other recursive functions which do not terminate. And this is very important because otherwise you don't have the full power of computability theory. So we are not speaking here about general recursive functions, but only those that can be defined by primitive recursion, and those terminate. And by the way, because we are in type theory, we want only things that terminate. So we could not hope to define general recursive functions. This is not in the rules of the game. The rules of the game is to remain in a world where everything terminates, even if I'm not going to cover termination aspects in the course. Okay, so this is the induction principle. Okay, and it has a version which is not dependent. Okay, I promised you to give you a dictionary from and to rec. So if I have a type, so let me go back to sigma type. Yes. Going from rec to int, rec is always a special case of int where we quantify over a type which is not dependent. So this line here has to be read as the special case of this line where this family here does not depend on A times B. So this is this is the difference between rec and int. So int here, the general principle is for a dependent family of types, but if the family is not dependent, we have the recursion principle, which is actually what is called primitive recursions in the book. Okay, but this is also primitive recursion, but the dependent version of it. Okay, the classical version is this one. Okay, so it's the same here, but you see that I have removed every references to 0, n, n plus 1. And if I remove these references, I have exactly this type. Okay. Again, here I remove this CZ and I turn this into n arrow C. Okay. And finally, we can even have rudimentary principle that is even more rudimentary than a rec. Okay. that does not use this number here. Okay, so this is called iteration. So you have also a principle that that consists. Okay, this principle is easier to explain than this one. It's simpler. So suppose let's do it intuitively. Suppose we want to define a function from n to c, knowing an element of c and a function from c to c. Well, the idea is that, for example, suppose this function, okay, so this is again a C0 here. This is a C0 and this is a CS, okay? And suppose I want to calculate, and this is my function f, which I want to compute. So the idea is that f of 3 is going to be CS of CS of CS of C0. So you start from C0, you do CS once, CS twice, and CS 3 times, because it's S of 3. If it is F of 4, you will apply it 4 times, etc. Okay, so now I'm going to completely discard these 2 slides. I just tell you the content of the slides, but will not comment on them because I want to continue on properly topics of homotopy type theory, and time runs. So this first slide is about defining functions of several arguments, because here we only define functions of one argument, okay? But usually if you know about recursive functions or primitive recursive functions, they are of several arguments. So can we encode n-ary functions using this principle? The answer is yes, okay? Because we have variations on the choice of the type family C, okay? So we can adjust our needs and find an appropriate type family, okay, to encode a recursion principle for binary functions here in terms of unary functions, just by switching from a type family C to another type family C prime defined in the appropriate way. Okay, this is this slide. And then you can also show that the simpler iteration, which I just checked here, is powerful enough to recover the general recursion. Okay, so this looks like more rudimentary, but in fact, it has the same power, and this is what is written here, okay? And then in the last quarter of an hour, I will discuss identity types more formally, and this will finish basically the exposition of the main type constructions. So maybe I jump directly here, okay, to what we need to know of the rest of the course. We need to know about sigma types. We need to know about sum types, about Booleans, about natural numbers, about pi types. Okay, I didn't write pi types here because pi types do not have an associated induction principle. Pi types have this application operator, which is a bit different from induction. So, so there you have also the pi types, and then natural numbers, and then propositional equality. Okay, so with this identity type, I will have finished the general presentation of the type formers of type theory. And we will start looking at different topics of homotopy type theory. Okay, so the identity type, there is a type former. Okay, so you can form, if you have a type, if you already have a type, capital A, if you have 2 elements of this type, then you can form the type propositional equality X equals Y. Then you have a unique constructor, well, family of constructors because it's parameterized by elements of A. So if you have a small a in capital A, then you have ref A of type A equals A. And then what is the induction operator? So this is what we will do in some detail because this is very surprising the first time you meet it. So we have to be also very slow. So the general idea is the same as before. We want to know how we can use a term, how we can define a function from an equality type. Here, sorry. Okay, so how can we form, given a type A, given elements X and Y of type A, given a proof that X is equal to Y, we would like to build an element in the type family C depending on X, Y, P. So let me read from the beginning. Suppose that we are given a type family that depends on X, Y, and P and returns a type. So this is a type family of the form CXYP. The induction principle tells me something very magical. It tells me, well, roughly speaking, but here we have to be very careful about the interpretation of what I'm seeing. Essentially, because the only constructor is ref, we want to give a careful axiomatization of the fact that the identity type contains only the reflexivity. Okay, but this is not true in general. We will see in later that, for example, we will axiomatize circles by providing explicitly a loop, a proof of equality of X equals X, which is not the reflexivity. So this is certainly not true. But something is true, which is that if we look at an element that is polymorphic or generic, that appears in all equality types, not a special one for a special X or a special Y, but if we look at the whole family of all equality types where X and Y vary over A, then generically, this family contains, morally speaking, only the reflexivity. The reflexivity is the only guy who is there everywhere somehow. That's the idea. That's the idea, which is not exactly true because reflexivity means it's between X and X. Okay, so okay, but this is the idea. So now formally. Now we read it formally, and formally it makes real sense because it's very precise. We want to find a function of this type, which I already described. For this, what I need to find is just a function that generically will take an element of X, a single element of X, and then provide an element of CXX ref X. So this makes precise this idea of genericity. So for all varying X, Y, P, the only relevant cases are the varying special case where I take X, X, and ref X. And this, if I know how to provide a value for all these X, X, ref X, then I know how to provide a value for X, Y, P in general. So this is the principle, okay? And we are going to see how we use it. Not today, or let me check, because I could do something different. Yes, I will directly go to an application of this principle, because otherwise it's too abstract. So let me switch the order. I will go directly here. Directly here. Yes, exactly. Okay, so I will do this slide and we will finish with this slide, because you will, with this slide, you will understand what is this induction principle. So by the way, it has a name. It has a name, it is called path induction. Okay, because remember that in the topological interpretation, proofs of equality, elements, inhabitants of equality types are paths. Okay. Yes, by the way, I answered one question that was raised also in the first session. People asked me, what is the the real topological interpretation of types? Okay, because I gave an analogy, but well, the course will not be about this, but I can give an answer. So there was one answer given by Pablo, I believe already, that for natural numbers, you will take, well, just natural numbers considered as a topological space, which means a discrete space. But for example, if you have, but the equality type is much more interesting. The equality type will be interpreted as, well, this is a big word. It will be interpreted as an infinite loop space. Okay, so it's a topological space with a lot of structure inside. Okay, which has a structure of higher groupoids and things like that. So the interest of the mathematical interpretation arises essentially by the rich structure of identity types, which will be interpreted by rich mathematical structures with lots of higher structures. But this is way beyond this course. So anyway, let's return to our first application of path induction. And I have 5 minutes for that. Okay, so I want to show you how I can define the composition or concatenation of two paths. Okay, so in logic, suppose that we think logically. Suppose we have proved x equals y and y equals z. Then by transitivity, we should have a proof that x is equal z by applying transitivity. So in homotopy type theory, we can derive, we don't need to axiomatize transitivity, we get it for free. I mean, we can define, it's not, we do not need to postulate, we can define the concatenation of P and Q, which will be a path from X to Z. Okay? So how do we define it? So you see that here X, Y, and Z are completely arbitrary. They are varying. P is arbitrary, Q is arbitrary. So we are in the typical generic situation I was describing before. So in order to define P concatenated with Q, I can safely restrict my attention to the case where P is a reflexivity. That's the first step. Okay. This is what path induction tells me. But again, I repeat, this is important because here everything is generic in the problem I want to solve. Okay, good. So the only thing I need to define is this guy. But again, Q is arbitrary. Hence, I can also apply path induction. The first thing was to apply path induction to P, but I also can apply path induction to Q. So the only thing that I need to check is whether there is sorry, the only thing I need to define is the concatenation of the reflexivity and of the reflexivity. And I have a very, very good candidate because the reflexivity is a proof here of x equals x. Okay, here it's a proof of x equals x, and I'm looking for a proof of x equals x. So I can take reflex. So you see here that in order to define P dot Q, I only need to define this for P and Q being ref, and then I define it to be reflex. Okay, and you can do the same trick to define what is the inverse of the path, because if you have a path from x to y, you want also to have a path from y, a path from y to x. Okay, because an equality is supposed to be symmetric. Okay, and it's the same idea. We want to define p minus 1. Okay, so this is a notation for the inverse. And in order to define p minus 1, we only need to define for it for ref. Okay, so we need to define what is the inverse of ref. But since ref is of type x equal x, okay, symmetrizing it gives still x equals x. So reflex is a very good candidate to be its own inverse. Okay, so it's like in group theory, you have the identity element, and the inverse of the identity element is the identity element. Okay, and finally, and I will stop here. Not only you can concatenate paths and give inverses of paths, but you can also check that these operations satisfy the axioms of a group. So remember that a group is defined by asking the operation to be associative, that's here, to have an identity element, which is a ref, and that inverses are inverses, which means that, well, if you concatenate P with P1, P minus 1, it should be ref, and the same thing here. So again, these are propositional equalities. And how do we prove them? Okay, so you see that in order to prove the group laws, we again will use path induction. So suppose, and this is really my final remark, suppose we want to prove this law here, the identity law on the right. Then, because this is completely parametric in x, y, and p, well, the x, y are implicit here. Okay, p is a term of x of type x equals y. Okay, and x, y, and p are arbitrary. It is enough if I want to provide a proof of it. Okay, it's enough to provide it in the case where p is rest. Okay, so we need to find, in order to prove this propositional equality in full generality, we only to prove it in this special case. But we just have defined concatenation in such a way that this guy is definitionally equal to the reflexivity. So what we are looking for is a proof of ref equals ref. And this is reflexivity. Well, it's actually reflexivity applied to reflexivity. Okay, because here we are dealing with homotopies. We are dealing not with proof of equalities, but proofs of equalities of proofs of equality. Okay, so this is everything for today. So we completed all the type constructions, and I tried to sketch the important role of path induction, and that's enough for D1. Okay, goodbye and thanks. And I will check the questions and try to answer them tomorrow morning.